All right, last week we talked about this one number that will give the centralness of the data. It could be mean, it could be median, in some very rare cases, mode, and a geometric mean. Now let's talk about this measure of variability. The story is this, right? You have a bunch of numbers, and if you could tell me one number to define that data, you told me the measure of centrality. Now, why would we need this measure of variability? Is a good example. Let me start with motivate with an example. Suppose there are two data sets. One data set is suppose you invest $1,000 with me, and I have a great scheme that will pay you $2,000 at the end of the year. $2,000, $2,000, $2,000. So every year you spend $1,000 and you get $2,000 back. Suppose, just make simple 6 years worth of data. Another, suppose you invest $1,000 this year, you get just $1,000 back. Another year you invest $1,000, you get $2,000 back. Another you spend $1,000, you get $5,000 back. Another you spend $1,000, you get only $0 back. Another you get $1,000, you spend $1,000, you get $1,000 back. Another you get $3,000 back. And again, the mean in the both side, if you take the sample mean here, this is 2,000. Right? The mean of same value of numbers is going to be 2,000. Here again, the mean is 2,000. If we just use mean to differentiate between this data set, there is really no difference. This has a mean of 2,000. This has a mean of 2,000. How do you differentiate between these two data sets, where here all the values are so close to the mean? Actually, they are exactly the mean. Here, the values are distributed around the mean. How do we separate this? How do we distinguish between these two data sets? That's the idea. That's the idea behind measure of variability. The first, real naturally, it should come to your mind is the range, right? The range is very natural way to describe this variability. Well, the data set you described has the mean of 2,000, and the smallest value is 0, and the largest value is 5,000. So basically, range is just the gap between the highest value and the smallest value. And it's a pretty good measure, actually. It's a pretty good measure of variation. The only problem with this is it only looks into two data points, the largest and the smallest. What happens in between doesn't tell a very good story of the data set, but it's a really good start. Right? Here, the range would be 0. The max is 2,000. The mean is 2,000. So the range is 0. Here, the range is 5,000. Telling, that number is telling quite a bit about the data. But let's improve upon this, right? Let's improve upon this idea of range. Again, range is very simple. The largest value minus the smallest value. Okay? Very simple. The first real candidate for this second measure of variability is variance. Okay? There are few nuances with this data set, this particular measure, but it is something you have used in the past, and the idea is this. It is the measure of how are the numbers distributed around the mean, right? The deviation of the numbers around the mean, but the problem in the variance is the deviation is squared. Okay, so the properties of variation really are few things. The first, obviously, is it is the deviation around the mean, which is what we really wanted to measure, right? Deviation around the mean, because we already have the mean as our first measure. So we're going to come up with something that improves upon that information. The second is it utilizes the whole data set, which is what improves upon the range. And the bad side of it, these are the pros. The con side is the deviation around the mean are squared, and we'll come back to that, why that is a bad thing. But let's first calculate this. What we do is we calculate the mean of the data, because that's the first moment, we already have it. And then for each value, for each data point, we subtract the mean from the data point, right? So if our values are, say, 2000, 3000, 4000, and 5000, and 6000, suppose, so the mean would be 4000, right? The mean is 4000. The mean is 4000. So what you would do is from each value you subtract the mean. So 2000 minus 4000, 3000 minus 4000, 4000 minus 4000, 5000 minus 4000, 6000 minus 4000. Okay. Then the reason this has to be squared is otherwise what happens is the negative numbers here, minus 2000, minus 1000 here, the plus 2000 here, minus 1000 here, that would cancel out. You don't want that, right? You don't want to cancel that out, the effect of being on the left and being on the right. So traditionally what has been done is there are other ways to do it, but people have chosen to make it square, right? So the square of 1000 is a number, a square of 2000 is a number, a square of 5000 is this 0 is a number, a square of this 1000 plus 1000 is a number, square of this plus 2000 is a number. You do all that, you add them all up. That's what this sign means. You add them all up. After you add them all up, you divide this by n minus 1. This is kind of a little bit different. You have 5 values, your n is 5, but you divide it with 5 minus 1. Now, the only caveat being if you know this is your population, that means that is the every data point that could exist, that's what you're studying. If that's what you're studying, you just divide it with the n instead of n minus 1. But for the most part, we only have sample. So if it's the sample, we do with n minus 1. The reason here, we don't want to go into the too mathematical detail of it, but somebody proved that for sample, that you subtracting from this minus 1 from the n gives you the best estimator. If you want to know details, send me an email. I'll explain you why this is a very elegant proof actually. But just remember this, if you have a sample rather than the population, we divide it by n minus 1 instead of n. Another way of thinking this is what happens when you make this denominator small by making n minus 1 is your value becomes, your variance becomes bigger. We'll do a smaller example. I'll do it in another video. And so that by overestimating it, by subtracting 1, you're overestimating the variance, and that is more desirable than underestimating it. But the idea is the cool properties of variance is you start with a mean of the data set, you subtract the mean from each data point, whatever you get it, you square it, you add that all up, and you divide it by n minus 1, n being the number of data points. That's the idea behind variance. Alright, let me stop it here.